Hello and welcome to Unit 4. In Unit 4, we're going to be discussing Newton's laws. Newton's laws are a set of 3 laws that govern forces. We're going to begin by looking at Part 1 with Newton's first and second laws. To start us off, let's think about the early ideas. What led to Newton's laws? In ancient Greece, we had Aristotle. Aristotle felt that everything had a natural motion. Things wanted to return to their natural places. So dropping clay to the ground. Clay wants to be part of the ground because it is a form of earth. Smoke and steam rise because they are air and they want to be up above where air exists. Any motion that countered the natural motion is violent motion. So if you picked clay up off the ground, that was a violent motion against the clay. These ideas persisted for quite a few years until a gentleman named Copernicus came along and started thinking about other things, like the fact that the Earth rotates around the sun and not vice versa. Copernicus's ideas were not met with a lot of favor, shall we say, and luckily for us, another gentleman named Galileo came along and took Copernicus's ideas and expanded upon them. And one of the things that Galileo said was that objects will continue moving in a straight line forever if there is no interaction with it. Now, you may be thinking, that's not what I observe. I know that if I roll a ball, it will, slow down and stop. If I push a block, it will slow down and stop. Everything I see in my daily life slows down and stops. But that's because all of these things have an interaction on them. They all have a force acting on them. Galileo's ideas were picked up by Newton and again expanded upon. Newton's first law is really a restatement of Galileo's idea of inertia. The idea that something will keep moving forever as long as it has no interaction. Newton's first law, in proper physics language, says that an object in motion will stay in motion with constant, possibly zero velocity, unless acted on by a net external force. In other words, an object will continue moving forever in a straight line at a constant speed as long as there's nothing interacting with it, which is a really hard thing to get to happen. It's really hard to eliminate all the interactions here on Earth. But we can use it as a thought problem, if you will, and we can do things like have the astronauts test it out in space. What happens then? Before we continue on in understanding Newton's first law, I'm going to do a little aside really quick, because with force, we get our first unit that isn't one that it's a combined unit rather than just a kilogram or a meter. So the unit of force is the Newton. By definition, 1 Newton equals 1 kilogram meter per second squared. Okay, so you can see how it is a combined unit. I really often put this down to being physicists are lazy. We don't want to write kilogram meter per second squared all the time, so we combined it down and named it in for the guy that did a lot for the field. Okay, so now returning to Newton's first law, an object in motion will stay in motion with constant, possibly zero velocity unless acted on by a net external force. In order to understand Newton's first law, we really need to understand what it means for there to be a net external force. So first off, what is a force? Well, it's a push or a pull on something. Okay? An external force is a force that comes from outside the object or objects that you're looking at. A net external force would be the sum of all of those external forces acting on whatever you're looking at. Okay, so it's a sum, but force is a vector. So what we really mean here is that it is a vector sum, which means you got to be worried about direction. So here I have 3 objects with forces acting on them. And I want to know what is the net external force on these objects. Well, if I look at object A, it has 5 newtons to the right, 3 newtons to left. Therefore, the net force on it would be 2 newtons to the right. If I look at B, it's exactly opposite. The 5 Newton force is to the left and the 3 Newton force is to the right. Therefore, the net external force on B is 2 newtons to the left. If I look at object C, we have 5 newtons in both directions. Therefore, the net external force on it is 0. So, given what we've just looked at, can we say that no force acts on a body at rest? And the answer to this is that if a body is at rest and going to stay at rest, then it has no net force. That comes from Newton's first law. Being at rest would be the case of 0 velocity. So there's no net force on it. Does that mean that there's no forces on it? Not at all. Think about yourself sitting probably in a chair watching this video. You're not moving, or at least not moving much, but you have gravity pulling downward on you. You have a force from your chair pushing upward on you. You may have other forces on you depending on what your scenario is, but at least those 2. So you have no net force if you are at rest. Here's another thought experiment. In order to slide a heavy cabinet across the floor at constant speed, you exert a horizontal force of 600 newtons. Is the force of friction between the cabinet and the floor greater than, less than, or equal to the 600 newtons? Okay, well, if you don't know me by now, you know that I like pictures. So here I am pushing on a big old heavy cabinet. And if I think of this cabinet, I think I have 600 newtons in the direction I'm pushing, and then friction going the other way. Now the question is, how do these 2 forces compare? Constant speed. I underlined it when I read it, and I'm going to box it in now. Constant speed. Technically, it should say constant velocity. That being said, constant speed. Remember Newton's first law. Object in motion will stay in motion with a constant velocity unless acted on by a net external force. We have the constant velocity piece here, constant speed. Therefore, since, I'll add the C here, speed is constant, that means the net force has to equal 0. The speed won't be constant if there is one, so since the speed is constant, there can't be one. Okay, if the net force is 0, that means that my 600 Newton push has to be balanced exactly by friction equal to 600 newtons as well. So the answer to the question is that the friction is equal to 600 newtons. This is an example of a special case. Equilibrium occurs when there's no net force acting on an object. Okay. Can an object be in equilibrium when only a single force acts on it? The answer here is a big old no. If you have only a single force, there is no way that you can sum things together and get 0, assuming that single force is not a 0, in which case it's really not much of a force, right? So no, you have to have more than one force in order to be in equilibrium. Or you can have no forces. That would also work, but again, that one is hard to achieve. Is an object in equilibrium stationary? The big heavy cabinet in the last example was moving at a constant speed with no force or no net force. So does it have to be stationary? No. It could be stationary. What it does have to be is at a constant velocity. Okay? Constant speed, constant direction. Okay. Newton's second law is really another version of Newton's first law in a lot of ways. It tells you what happens if there is a net force. Okay, so Newton's second law says that the net force on an object is equal to the mass multiplied by the acceleration. F net equals ma. Sometimes you might see this written as the sum of the forces equals ma. Remember, this is the mathematical symbol for summing. Okay, I tend to prefer this notation. And notice it's a vector equation. So again, we have to worry about directions. I said it as I introduced Newton's second law, that it really is just, in a lot of ways, Newton's first law again, or vice versa if you want to think about it. If the acceleration is 0, then the velocity is constant, and the net force is 0. So we're back to, if there's no net force, the velocity has to be constant. First law and second law very much go hand in hand. Okay. Now, forces are vectors. So now let's think about having two forces. So let's say F1 is 3i hat minus 4j hat. And F2 is negative 2i hat plus 6j hat. If I want to find the net force on this object with F1 and F2 on it, I add those forces together. Okay? But my x direction does not influence my y direction. So I end up with 3 minus 2 in the x direction plus negative 4 plus 6 in the y direction, which is 1 I hat plus 2 j hat. Okay. So remember, when adding forces, they are vectors. You need to consider directions, and you cannot add something in the x direction to something in the y direction. This concludes this part of Unit 4.